All right. Now, Rutherford's alpha scattering experiment, if you recall from freshman chemistry, that's what led to the notion that the atom has a very tiny nucleus, and you've got those electrons going around that nucleus in a very, very large space compared to the actual space occupied by the nucleus, right? We said that at the very least, the electron cloud, the region, that mostly empty region around the nucleus has a diameter of at least 1,000 times bigger than the nucleus itself. So you're looking at a billion times bigger volume. 1,000 cubed is about a billion, 10 to the 9. A billion times bigger volume, bigger empty volume compared to that occupied by the nucleus. Now, there's a problem with that at the time. Okay, experimental evidence suggests that that is the way atoms are. You have a nucleus and electrons around the nucleus, and mostly empty space. But the problem with that, based on classical physics, is they know that if you have electrons going around in circles around a nucleus, those electrons are accelerating. And when you have a charged particle that's accelerating, okay, a particle that's accelerating will emit light, will produce light. So as an electron's accelerating around your nucleus, it's going to be producing light. So if it's producing light, it's losing energy. So if it's losing energy, what will happen to it? Eventually, it will crash into the nucleus. In fact, it will crash, classical predictions that it will crash into the nucleus so quickly that the atom as we know it could not possibly exist. So the resolution to that eventually was to say, okay, classical physics is wrong, okay? But there were earlier attempts to explain that. The Bohr model, okay, assumed that there must be some allowed orbits for electron for some reason. Okay, he didn't say he didn't try to say what the reason was, but he said there must be some orbits around the nucleus that is allowed for the electron. So that was the Bohr model. So that model of that so-called planetary model of an atom that you've seen in your early courses, that's the Bohr model. Okay. So Bohr basically suggested that there must be some specific orbits for the electron where for some reason it's allowed. Okay? And so Bohr's model was successfully used to explain, for example, the spectrum of the hydrogen atom. Based on these orbits, Bohr calculated what the energy of the electron would be, and then transitions from one allowed orbit to the other led to the correct prediction for the known spectrum of hydrogen. Okay, so that was one of the successes of the Bohr model. Unfortunately, the problem with the Bohr model is it works only for hydrogen, and it could not explain finer details. If you look at the spectrum of hydrogen at higher resolution, you cannot explain why those finer details are there. So, but Bohr was the first to propose the notion of quantization for the energies of the electron in an atom to explain it. Okay, so anyway, Bohr's theory about what the atom is, the planetary model, is now referred to as old quantum theory. Okay. Now, de Broglie was able to make a justification, sort of, for the Bohr model by proposing that the electron is a wave. Okay, and the idea in that case was sort of the justification for those stable orbits was to say that if you have one orbit that's allowed, okay, then it must be because the circumference of that orbit is a multiple of the wavelength of the electron. And so if you have a multiple of the wavelength of the electron, then you don't get destructive interference of the wave around that orbit. Whereas if it's not a multiple if the circumference is not a multiple of the wavelength, but you'll see, for example, let's say you start over here and you have a wave, okay? Then you may not end up there, so you would have all of this, and so you'd have destructive interference, essentially. In cases where you get destructive interference, you have a disallowed orbit. In cases where you have constructive interference, where the wavelength is where the circumference is a multiple of the wavelength, then you have a stable orbit. Of course, like I said, that model is no longer accepted because the Bohr model suggests a very precise, well-defined orbit, which is no longer acceptable. As you've seen, one of the consequences of the wave behavior, wave nature of the electron is the uncertainty principle. You cannot precisely determine both position and momentum of the electron simultaneously. Okay? So, in other words, this classical prediction that would predict how the electron would actually crash into the nucleus is simply wrong. It's not acceptable. That's not the way nature is. Okay, so it's the classical theory that failed to explain that. So we have to come up with a new theory to be able to explain